the geographical perspective. So when we think about geographical perspective in terms of computers, in terms of R also, we basically need to start with this question. How we can represent the real world with objects on our computer. How can we do that? And just to underline, we will simplify stuff. We won't just take the real world and try to get every piece of grass from this place and try to put it on the computer. We'll do some kind of a simplification. And in general, when we think about it, we can think of some data models. There are two most prevalent data models, spatial data models. The first one is a spatial vector data model. So the spatial vector data model is the idea that we describe the world, so we describe this area that you've seen on the previous picture by trying to create discrete objects. So we try to create points or line streams or polygons. So those objects can represent like locations of the buildings or roads, rivers. They can represent borders of the countries, etc. So the general idea here is that it's very simple. We have points, and each point has a pair of coordinates. So we have some x coordinate, we have some y coordinate, and then we have another point, another set of coordinates, etc., etc. And then if we want to create a line, we just create many points. So the first line is just connection of 3 points. So there is a first point, then the straight line to the second point, that's a straight line to the third. And this is how we create a line. So how we can expand it to polygons? The same, but here we have a polygon, so the polygon number 1. So we connect the first point to the second, to the third, to the fourth, to the fifth, and we repeat the first point again. So this way we have a polygon. And each of the types of those objects, they have different properties. So for the points, we cannot do a lot of things. But for the lines, for example, we can calculate what's the length of the line. And for the polygon, we can calculate what's the perimeter of the polygon or what's the area of the polygon. And then for each of those types of data, we can have a data frame if we speak in our language. So each point or set of points can be connected to a row in a data frame. And the same for lines or polygons. We can connect each spatial object or geometry. So those are geometries. We can connect them to attributes. So we have coordinates and we have data frame. And you can see that in R, the most popular implementation of this idea in R currently is the SF package. So we can read some spatial data into R. And if we just type the name of the object, we'll get this kind of a summary. And you will quickly see that the bottom part is probably very familiar to most of you. It's just a table or extended data frame or sometimes just a data frame. So we have a data frame with just ID 1, and another column is a geometric column. So this is a column with all of the coordinates of the points creating this line. But with spatial data, we have a few more things to consider. And you can see them here. So we need to consider the geometry type that you've seen before. We often think about bounding box. So bounding box are basically what are the extreme coordinates of our area. And we have CRS, coordinate reference system. And I will be back to the idea of the CRS later during this talk. So that was the vector data model. And the second most popular model for spatial data is the raster data model. So with raster data model, we try to represent world by continuous fields. So instead of having discrete objects, we have continuous fields. So we have an area, and for each element of this area, we have some value. So here we can see that we can represent continuous data like elevation, like temperature, etc. Or we can represent categorical data, like land cover or soil types, and so on. And if you just want to build a little bit of intuition about raster model, you can think of it, it's a simplification, but you can think of it as a matrix. So we have a matrix, we have some IDs of our cells, and for each cell we have some assigned values. And then the final map is just representation of this matrix in a visual form. So by assigning a color to a value. And in R, we have a few packages for that, including a package called stars and a package called Terra, and I will show you Terra here. So I have a file in a GeoTIFF format. So this is a format for spatial raster data. I read this file and open it in R, so just type the name, and you can see we are getting some summary. There is no data frame here. This object is actually just a pointer to the data. So we are not even reading this data into our memory. And here you can see some information like dimensions. So what are the sizes of our simplifiedly say matrix? So you can see that our matrix is 1400 by 1100 when it comes to row and columns. So 14 by 11 with the resolution of 1000 by 1000. So in this case, 1000 means 1000 meters by 1000 meters. So each cell of our raster is 1000 meters, 1 kilometer. Then we have an extent of the bounding box. We have again CRS and some other information about, for example, minimum and maximum value of our data. And everything, so the actual raster and the matrix, of course, is regular. So it's not like it starts here and ends up here. It starts here and ends up here, but those values here are just NAs. I mentioned that we have this vector model, we have this raster model, but this is not yet. So we have more ideas, but which are less often used, but can be used in very certain situations. So we can think also about data cubes or spatiotemporal arrays. So we can think about connecting also space and time and type of the sensor or type of the variable. We can think about meshes. We can think about point clouds. So there are also different types that I mentioned before. And gladly, for those different types, we have some R implementations. So we also can work with those different types of data in R in a fairly simple fashion. Like with those data cubes, we have the stars package. For the LiDAR data, we have the point cloud data, we have the LiDAR and LASAR packages and so on. I promise that I will go. I will get back to this topic. So this is, I think, the topic from the geographical perspective that people try to avoid as much as possible, and maybe shouldn't, or at least maybe it would be good to just try to get the basic grasp of the idea. Because when we think about coordinates, because I mentioned you, if you have a point, it's just a pair of coordinates. But this pair of coordinates can be very different. So for example, I'm standing here and I can say, okay, so my coordinates are now 0 by 0 because I create my own system. And now if I move a step here, I can say my coordinates are 0, 0 by 1 from the origin point. And this could be useful for some cases when I just do some studies in one area. But if I want to connect my data with other data sets, probably it would be better to have some common coordinate reference system. And because of that, many coordinate systems exist. Another thing to consider are geographical coordinates and projected coordinates. So geographical coordinates are the coordinates, if you think about space in terms of longitude and latitude. Because this is the degree this is measured in degrees, and we can say that, for example, let's say this location is 0, 0 by 0, and this one would be like 50 by 0, and so on. The issue with geographical coordinates is that you cannot use simple math to just calculate the distances. And hopefully you can see that here, that the distance of, let's say, 1 degree from here to here is different than the distance from 1 degree to here to here. And that makes some problems, some issues. And that's why people often use projected coordinates. So the idea of projected coordinates is like this. We just take our planet and we try to find a way, so we use some kind of a projection technique to project the information from the sphere into a flat surface. There are many techniques to that. I won't go into the details, but this is the whole idea. But when we are doing that, we are helping each other and ourselves often, because then the distance from here to here and from here to here could be, depending on the projection, constant or very similar. The problem is that when we project our data, we create distortions. So we can distort areas, we can distort angles, we can distort shapes and distances, etc. And you can see that on this visualization of the graph. So in this animation, when we look at Greenland, so if you think about this animation, you stop that when the Greenland is the largest, is the Mercator projection, which is great with angles. It was used for sea travels, so it's, I think, connected to Sevilla in a sense. But this projection distorts areas a lot. So you can see that Greenland could be as big as Africa, when in fact it's many times smaller. And this is why I want to highlight this challenge when working with spatial data, that you need to